লাগিয়ে নিতে হবে। সমস্যা কাছে যত বেশি সামনে আনবে মাথা কেটে যাবে। এদিকে আলো কাটতে হবে না।
This is visible. Please tell me. Am I audible or and this is visible? Please tell me. Hello. Is it visible? I am audible. Please tell me. Okay. Thank you. Thank you. Okay. So today I discuss spanning set. Suppose Sohini, if suppose V is a vector space, let A be any set, or I think it is better to write subset of A V, any subset of V say A has an element, then is A, this is a linear span of set A okay. Okay. Now is it visible? Unushka, is it visible now? Please tell me. Anushka, Suhini, Subhrojit, is it visible now? V. Yes, okay. Let V be a vector space. A be a subset of V Kakule, I think now it is visible. Okay. Okay, thank you. V be a vector space, A be a subset of V, say A contain n elements, x1, x2, xn, then SPA, this is a linear span of set A, that is the collection of vector which is a linear combinations of x1 x2 xn, where Ci belonging to R, I from 1 to small n. So this is called linear span. Now my claim is this SPA is a subspace of V, subspace of V. So proof, take two vectors, say x curl, y curl belonging to SPA. Since x curl and y curl belonging to SPA, this implies x curl can be written as a linear combination of x1, x2, xn vector, and y curl also written as a linear combination of x1, x2, xn curl. Yeah. So where Ci di is belonging to R, I from 1 to n. We know if SPA is a subspace of P, if and only if you take any two vectors, say x curl and y curl, if x curl plus lambda y curl belonging to SPA, then SPA is a subspace of V. So now we take x curl plus lambda y curl, where lambda belonging to R, since x curl is a summation I from 1 to n Ci xi curl plus y curl is a lambda I from 1 to n di xi curl, then this equal to sum over I from 1 to n Ci plus lambda di xi curl. Since this is a scalar, Ci plus lambda di, since Xci, lambda di all are scalar, so we denote this Ci plus lambda di by Hi, say, where Hi equal to Ci plus lambda di. So hi belonging to R for all I from 1 to small n. So this means so is it the only problem of Pallavi or everyone? Tell me. Now it is clear? Pallavi? Okay. I think so. Now x curl plus lambda y curl, which is again a linear combinations of, this is a linear combination of x1 curl, xn curl. Hence, this implies x curl plus lambda y curl belonging to SPA. So therefore, SPA is a subspace of V. For example, suppose I consider RQ. We know this RQ is a vector space under usual vector additions, that is element-wise additions, which I already defined in my previous classes, and usual scalar multiplications. If I take any two vectors from RQ, say it is A, I take two vectors, say 1, 1, 0, 1, 0, 0, then here SPA is a linear combination of these two vectors, C1 1, 1, 0 plus C2 1, 0, 0. So this is C1, C2, C1, 0. So in that situation, SPA is the collection of this type of vector. So you can see that this is nothing but a so this is R cube. So this vector is nothing but any point, collection of the points lies in this surface. Okay, so since this is a vector subspace, generally, because here we consider a general vector space Rn, and this is a particular case, hence SPA is a subspace of R. So this is the constructional method of, this is just a constructional method of subspace of a vector space. Now, definition: a set of vector is set of linearly independent vector is called set of linearly independent vector. It is better to write that way. It's called set of linearly independent vector if and only C1 X1 curve. I think it's better to write in that way. Suppose since SPA is a subspace of V, okay, since SPA is a subspace of V, so zero curve, which is a null element or null vector belonging to SPA. So we know SPA is a collection of vectors which is written as a linear combinations of the vectors in A. A contains x1, x2, xn. So it is always possible C1 x1 curve, C2 x2 curve, Cn xn curve equal to 0. Why? Because 0 curve belonging to SPA is because SPA is a vector subspace, and we know vector space contain null element or null vector, and since SPA is a linear span, so it is always possible we can write Cx1 curve plus C2x2 curve plus Cnxn curve equal to 0 curve. And the trivial solution is all Ci 0 for all. This is a trivial solution. Now the question is, so forget about this definition first. I come to the definition later. So this is a trivial solution. So now question is it the only solution? That means the only way is all Ci 0, then this case happen, or for some Ci non-zero, this thing is happening. So if there exists some set of solution, that means if there exists some Ci non-zero for which summation Ci xi curve equal to null vector, in that case, without loss of generic, say C1 not equal to 0, then Then since C1 not equal to 0, we assume that because if this thing happen for some Ci not equal to 0 such that summation Ci xi curl equal to 0 curl, so without loss of clarity we can assume C1 not equal to 0. In that case we can write x1 curl as a linear combinations of other vectors, that is x2 to xn curl. Since C1 not equal to 0, write C1 by other scalar. So it means x1 curl also belonging to also written as a linear combination of x2 xn. So in that situation, set A is not linearly independent, rather it is linearly dependent, because the element of A, that is x1 curve, can be written as a linear combinations of summation of x2 to xn curve. Hence, hence, I denote this is equation number 1. Hence, we developed two definitions from this discussion, that is definition 1. Set A which contain element x1 curve, x2 curve, xn curve is a set of independent linearly independent vectors, set of linearly independent vectors if and only if one all Ci zeros, if and only if all Ci 0 for all I. That means one satisfied when all one satisfies if and only if one satisfies when vectors when one satisfies if and only if Ci 0 for all I from 1 to n. So A is a set of linearly independent vectors when one satisfied, one means these equations satisfied when all Ci is 0. So otherwise that means there exists at least one Ci not equal to 0 such that summation Ci xi curl equal to 0 curl. So otherwise set A is linearly dependent vector. Set of linearly dependent vectors is a set of linearly dependent vectors. So please tell me if you have any doubt up to. Please tell me, I am waiting. Okay, thank you. V is a vector space S and T both are subspace spaces of V. Now, this is a direction S plus T. We define this set as collection of V curl such that V curl equal to X curl plus Y curl, where X curl belonging to S, Y curl belonging to T. Okay. Now the claim is this S plus T is a subspace of V. So S plus T is a subspace of V. For proving this, we take two vectors, say V1 curl and V2 curl from S plus T. Since V1 curl and V2 curl both belonging to S plus T, this implies V1 curl can be written as a linear combination of X1 curl plus Y1 curl, where X1 belonging to S, Y1 belonging to V. Sorry, Y1 belonging to T, and V2 X2 curl plus Y2 curl, where X2 belonging to S, Y2 belonging to T. Now, V1 curl plus lambda V2 curl, this is equal to X1 curl plus Y1 curl plus lambda X2 curl plus Y2 curl, X1 curl plus lambda X2 curl, Y1 curl plus lambda Y2 curl. So, since S is a subspace of V and X1 curl, X2 curl belonging to S, this implies X1 curl plus lambda X2 curl is belonging to S. Similarly, T is a subspace of V and Y1 curl, Y2 curl belonging to T. This implies Y1 curl plus lambda Y2 curl belonging to T. Since X1 curl plus lambda X2 curl belonging to S and Y1 curl plus lambda Y2 curl belonging to T, this implies This implies this V1 curl plus lambda V2 curl belonging to S plus T. Hence, S plus T is a subspace of V. Proof. If you have any doubt, tell me. Thank you. So, my next claim is span of S union T. We already see that S union T is may not be a subspace of V, but linear span of any vector which is a subset of V is a vector space. So this is a vector space SP S union T. This is nothing but S plus T. This is nothing but S plus T. So S, any vector V which belonging to S plus T, this implies V can be written as a linear combination of X curl plus Y curl, where X curl belonging to S, Y curl belonging to T. This implies X curl Y curl belonging to S union T, because X curl belonging to S, Y curl belonging to T. This means X curl Y curl belonging to S union T, and X curl plus Y curl is a linear combination of X curl Y curl. So this belonging to SPA, S union T. Hence, S plus T is a subset of SPA S union. Similarly, take before proving other part, that means S SPA S union T is a subspace of S plus T. I define basis of a vector space. So we know the spanning set or generating set. I denote this set by capital A. Basically, this set, if you take a linear combinations of the elements of this set, this give a linear set which is a subspace. So, but question is it we need these n vectors? or less number of vectors to generate this SPA. So suppose, so I consider an example. Suppose I take R cube, I take vector A, I take a set A, which is contain three element. So this three element generate a vector space SPA this is nothing but a all the elements lies in this surface. So this is the SPA. So my question is, for generating this vector space, we need these three elements or less number of elements, less number of vectors. If we check that 1, 1, 0, this is nothing but a linear combination of these two vectors. So this is a dependent vector. So if you take another set A1 which contains only these two elements, in that situation you get this subspace. So, and if you take another set 1, 0, 0, one, 1, 0, in that case you get same space. If you span this linear, take a linear span of these two sets. So, and in that situation, you see that this vector cannot be written as a linear combination of another vector. Hence, these two vectors are independent. So, these vectors are independent, but in this case, these sets are not independent. But all these three situations, all three sets are generating set of this vector space. So the basis is a minimum number of generating set we prove it generally later. First, I define this vector basis. So this is a minimum number of generating set, or if you eliminate this, you take another subset A3 which contain only one element, that is 1, 0, 0. This 1, 0, 0 does not give this vector space. This give only the points which lies on this line, the collection of the points which lies on this line. So this is not the same as this. This is a subspace of this vector space. So therefore, this is the maximum number of independent vectors, collection of independent vectors which generate this vector space. So either this or maximum number of independent set of independent maximum number of independent vector which generate a vector space. So therefore we can define basis of a vector space. Let set A, which is collection of an element, be a basis of a vector space P if one A is a generating set of V and 2 A is a set of linearly independent vectors. Yeah. So basis of a vector space is a set of vectors which generates vector space as well as is a set of linearly independent vectors. If you combine these two things, then you get this is a minimum number of generating set or maximum number of independent set. Moreover, we observe that the basis of a vector space is not unique. If you look at A1 and A2, both are independent, both generate same vector space, but the vectors are not unique because in set A1 contains 1 0 0 0 1 0, in A2 1 0 0 1 1 0. So the basis of a vector space is not unique. Yeah. We will discuss the related result later, but up to that, the definition portions, is it clear for you or not? Please tell me. Please tell me, is it clear? The definition portion is clear, basis? Okay, thank you. So now the next part, that is SP S union T, I want to prove these portions S plus T. Okay. So take, since S is a subspace of V, so it has a basis. Say x1, x2, xs. T is a subspace of V. Consider is a basis of T. Now, so any vector you card which belonging to, so now take two vector x card which belonging to S. This imply x card can be written as a linear combination of Ci xi card and y card belonging to T. This implies y card written as a linear combination of di y card. Now x card plus y curve which is a linear combination of SCI xi curve and see that x1 x2 xs the basis of S and y1 y2 yt is a basis of t. This means x1 to yt all these vectors also belonging to S union t. And SPA S union t means this is a linear combinations of the vectors in S union t. Hence, these vectors, which is a linear combination of S union t, belonging to SP S union t. Therefore, x curve plus y curve, which is a linear combination of this vector and this vectors belonging to SPA S union t. This means x curve plus y curve belonging to SPA S union t. Since x curve y curve belonging to S union t, this means x curve plus y curve belonging to S plus t. Therefore, SPA S union t is a subset of S plus t. We have already seen that S plus t is a subspace of SPA S union t, and here we see that SPA S union t is a subspace of S plus t. If we combine these two, we get SPA S union t equal to S plus t. Proved. So please tell me if you have any problem. Tell me, I am waiting. Okay. Now inner product space. First I define inner product. So inner product an inner product on vector space V and inner product on a vector space V over, instead of R, I generally define this over F is a field, is a mapping, is a map X curve Y curve to X curve Y curve from P cross P Cartesian product to F satisfying or satisfying the following conditions. One, x curl y curl is a conjugate sign alpha 1 x1 x alpha 1 x1 curl alpha 2 x2 curl y curl equal to alpha 1 x1 curl y curl plus alpha 2 x2 curl y curl, and last condition x curl this is greater than equal to 0 and equality holds if and only if this scalar product equal to equality hold if and only if x curl equal to 0. For now, if you have any problem, tell me. Which part, for now? For now, I am waiting. Tell me which part. So, inner product is a, we denote this by, denote in this way. This is a mapping from V cross V to F, which satisfy these three conditions. So, if you take, so you can define inner product so many ways. In our situation, if you consider V is a, if you take V equal to Rn, and in our case I consider F equal to R, so x curl is nothing but a point in n-dimensional space, therefore x contain n component. Now, at the end of the class, I will discuss this portion, okay? Because I already complete this thing. So, please tell me at the end of my class. Please tell me your doubt. I will definitely discuss. Okay, thank you. So, x1 to xn, x curl is a n component and y curl which contain y1, y2, yn. Then the scalar product or inner product, this inner product is nothing but a scalar product which is defined as xi, yi, I from 1 to n. And we can easily check that this is obvious because it is required only when we take a complex number. Otherwise, for real number, this is always true. This conjugate part. 2 and 3 easily you check these portions. If you define your inner product in that way, you see that 2 and 3 always true. So this is nothing but this scalar product is nothing but an inner product. This is the example of inner product. You can define your inner product so many ways. So if you keep it this, the point is your inner product should satisfy these three conditions. If your inner product satisfies these three conditions, then you can say, only then you can say that this is an inner product. So a vector space a vector space, a vector space, a vector space together with vector space together with a inner product is a inner product space. Is called an inner product space. So this Rn is nothing but a inner product space where we define the inner product as summation I from 1 to n xi y. Okay. So before going to the next portions, I answered the Swarnago's question. Okay, Swarnago, you asked me these portions. Okay, the S plus, first of all, SP S union T is a subspace of S plus T. Clear? Is it your question? Okay. So since S and T both is a Swarnago, are you hearing me? So S is a subspace of V. It has a vector, it has a basis, and we assume that x1 curl, x2 curl, xs curl is a basis Swarnava, are you there? I am answering your question. Okay, thank you. So x1, x2, s is a basis of S. Clear? Next, T is a subspace. It has the basis y1, y2, yt is a basis of T. So this vector x1, xs, these are basis of S, means this belonging to S. Again y1, yt, this belonging to T. So this implies this belongs to S union T. So now clear? So SPA, if you take the linear combination of this, so this linear combination, because this belonging to S union T, so this linear combination also belonging to SPA, because SPA is a linear span of S union T. So up to that, Swarnamu, clear or not? Tell me. Please tell me, Swarnamu, up to that portions, is it clear for you or not? Swarnamu? Before going to the next step, please tell me, is it clear or not? Okay, thank you. Next. So this portion belonging to SP S union. Next, this implies, so this is a basis of S. So this portion is a linear combination of basis of S. So this portion sum over I from 1 to S. We denote this linear combination by X card. This X card so this X curl is nothing but a linear combination of the basis of S. So this X curl belonging to S. Clear for now? Again, this is a linear combination of the basis of T. So this is, we denote this linear combination by Y curl belonging to T. So X curl plus Y curl belonging to S plus T. So we see that starting with this portion, this X curl plus Y curl belonging to space union T, which implies X curl plus Y curl belonging to S plus T. Hence, space union T is a subspace of S plus T, and we have already proved that S plus T is a subspace of space union T. If you combine these two, this gives space union T is nothing but a S plus T. Clear, Sharnabu? Tell me. Sharnabu, are you there? Please tell me these explanations okay for you or not? Thank you. Two vectors, let V is a inner product space. Two vectors x1, x card, y card belonging to V are said to be orthogonal if inner product or scalar product, since I consider real Rn, so you can tell this a inner product or scalar product. So this should be 0. So two vectors x car y car belonging to V are said to be orthogonal if this thing is happening. So a set of vector x1 car, x2 car, xn car is the set of orthogonal vectors if all are mutually orthogonal. if all the pairs, inner product of all the pairs equal to 0 for all I not equal to j. So result, the set of orthogonal vector vectors is always linearly independent. A set of orthogonal vectors x1 to xn curve is always linearly independent. We always write C1 x1 curve, C2 x2 curve Cn xn curve equal to 0 curve. Now let y curve equal to C1 x1 curve, C2 x2 curve, Cn, or it is better to write in that way. So x curve, x1 curve, 0 curve. First we write this set C1 x1 curve plus Cn xn curve equal to 0 curve, or it is, I think it is start within that way, contradictory proof. Suppose x1 curve, x2 curve, xn curve is not linearly independent. That means there exists some Ci not equal to 0 such that C1 x1 curve, C2 x2 curve, Cn xn curve equal to 0 curve. We assume that C1 not equal to 0. So now zero equal to 0 curve x1 curve, inner product of 0 curve x1 curve equal to C1 x1 curve, C2 x2 curve, Cn xn curve. Since we know this linear combination equal to 0 curve, just we replace this 0 by this. And using the conditions 2 of inner product space, inner product, so we can write this C1 x1 x1, C2 x2, x1, Cn, xn, x1, since x1, x2, xn is orthogonal vectors, the inner product of xi and x1 where I from 2 to n equal to 0. So this is nothing but a C1, x1, x2. Since x1 is a non-null vector from third condition of inner product, we see that this x1 inner product of x1, x1 greater than 0. So this implies C1 equal to 0. Hence, this is the contradictions of our assumptions, because we assume that C1 not equal to 0, which is a contradiction. Hence, our assumptions is wrong. Therefore, x1, x2, xn is also set of linearly independent vectors. But converse is not true. That means a set of linearly independent vector may not be a set of linearly independent vector may not be set of orthogonal vectors. Example, you see that if you consider your vector space V equal to R cube, then we see that this is a linearly independent vector, but this is not a set of orthogonal vector. Just check these two. You see that the inner product of these two is 1. Hence, this is not a set of orthogonal vector. Therefore, we conclude that the set of orthogonal vector always linearly independent, but converse may not be true. Clear? Can I wrap this portion? Tell me. Tell me someone. Can I wrap this portion? Or wait? Okay, thank you. Okay. Next phrase, right? x1, x2, xn be a set of dependent vector if and only if there exists k where k lies between 2 to n such that xk curve belonging to linear span of previous vector, that is x1, x2, xk minus 1. Okay. So this result tells you a set of dependent vector x1, x2, xn be a set of dependent vector if and only if there exists a k, the k lies between 2 to n such that xk can be written as a linear combination of x1 to xk minus 1. This means xk written as a linear combination of x1 to xk minus 1. Proof. First if part. So if part tell you there exists a k, there exists a k, there exists a k such that xk written as a linear combination of x1 to xk minus 1. So you can write this as obviously for at least, you should mention this thing, for at least one CI not equal to 0 where I from 1 to k minus 1. So among these CIs there exists at least one CI not equal to 0 such that we can write this. So we write this thing equal to 0 curve. We add other vectors as follow. So this is equal to this. So then we see that there exists some non-null, non-zero constant. Here we see that we represent this linear combination as summation di xi curve I from 1 to small n equal to 0 curve, where di equal to ci, where I from 1 to k minus 1, and dk equal to c minus 1 and dj equal to 0, where j equal to k plus 1 to n. Clear? So then we see that there exists at least one di not equal to 0, because dk already minus 1. This means there exists at least one dk not equal to 0. Even dk to minus 1, even we see that from d1 to dk minus 1, some di's are not non-zero, because we assume that for at least one ci between c1 to ck minus 1 non-zero. So this means this thing satisfied when some di is non-zero. This implies x1 to xn curve is set of linearly independent vectors. Set of linearly independent vectors. LIN, linearly independent. Next part, that is only if part that means x1 to xn the set of linearly independent vectors is given. We want to prove that there exists a k which k lies between 2 to n. That is, we want to prove that this portion is given only part. That means x1 to xn is a set of linearly independent vectors. This is given. Our job, we want to prove that there exists a k which k lies between 2 to n, such that xk can be written as a linear combination of x1 to xk minus 1. So since this thing is a set of linearly dependent vector, one thing I need to rectify this thing. This means this is a set of linearly dependent vector. Set of linearly dependent vector, not independent vector. This is my mistake. Sorry. Please rectify this thing. This is a linearly dependent vector. LD, linearly dependent vector. I write it in short. You write in full form. Linearly dependent vector. So since this is a linearly dependent vectors, it's a set of linearly dependent vectors. So you can write this as C1 x1 curve, C2 x2 curve, Cn xn curve equal to 0 curve for at least one Ci not equal to 0. For at least one Ci not equal to 0. So define a set. This set is a collection of index I, collection of those index for which Ci not equal to 0. And since This is a finite set. It has a supremum. Sup over I, and this supremum number set is K. So K equal to supremum of the set, which is a collection of indices such that the corresponding Ci is non-zero. And this is possible because this is the set of linearly dependent vectors. And this implies if you write this linear combination and this linear combination, if this linear combination equal to null, this means there exists some Ci which is non-zero, because this thing is happening, that is for some Ci not equal to 0. So you always get this set which is a non-null set, and because this is a finite set, it has a supremum, and we denote this supremum by K, and this implies Ck not equal to 0, and since this is a maximum, so after that Ck plus 1 equal to 0, Ck plus 2 equal to 0, and Cn equal to 0. So using this fact, denote this by 2, using 1 and 2, right? C1 x1 curve, C2 x2 curve, Ck xk curve equal to 0. Since Ck not equal to 0, that means xk curve equal to minus C1 by Ck minus C2 by Ck So this means xk curve belonging to SPA spanning set of x1 xk minus 1. Hence proved. So if you have a doubt, please tell me. I am waiting. Please tell me if you have any doubt. I am waiting. Tell me. Tell me if you have any doubt. Anybody tell me? Swarnabh, Anushka, Subhrojit, tell me. Dishari, if you have any doubt, tell me. I'm waiting. No, sir. Okay. No doubt. Thank you. Thank you, Shubhodit. So, you know the Graham-Smith orthogonalization. So, let's briefly discuss this thing. Graham-Smith orthogonalization technique. Graham Smith. G.S. Graham Smith optimization technique. So, suppose we have set of independent vector and our problem is to construct set of independent vectors. Our problem is to construct set of orthogonal vector beta 1, beta 2, beta n be a set of orthogonal vector from this set of independent vectors. So for this construction of orthogonal set of orthogonal vector, we use Gram-Schmidt optimization technique. This method tells you first you set beta 1 curl equal to alpha 1 curl. Next, beta 2 curl equal to alpha 2 curl plus C 2 1 beta 1 curl, and since beta 1 beta 2 is orthogonal, we already know the scalar product of beta 1 beta 2 should be 0, and this is equal to so this implies C21 equal to minus beta 1 alpha 2 by beta 1 inner product. Therefore, beta 2 curl equal to alpha 2 minus beta 1 curl alpha 2 curl beta 1 curl into beta 1. Similarly, for beta 3, you write this alpha 3 equal plus C31 C32 alpha 2 curl C33 alpha 3 curl using same method as alpha. Sorry, this is, it should be beta 2 curl and beta 1 curl. Using same technique, we get this is nothing but a beta 2 alpha 3 beta 2 alpha 3 beta 1 beta 1 beta 1 beta 1. So generally beta r curl, this is equal to alpha r curl minus sum over j from 1 to r minus 1, alpha r beta j curve, beta j curve, beta j curve, scalar product beta j, where r from 2 to n. So this is the procedure of constructing orthogonal set of orthogonal vectors from set of linearly independent vectors. So if you have any doubt, tell me. Tell me. If you have any doubt, tell me. Thank you. Next result. Number of vectors in a spanning set or generating set is greater than equal to number of vectors in a set of independent vectors. And here independent means linearly independent. Proof. V is a vector space. This is a alpha 1, alpha 2, alpha n. We assume this is a generating set or spanning set of vector space V, and beta 1, beta 2, beta t is a set of linearly independent vector in V. Since beta 1 to beta t is a set of linearly independent vectors in V, this implies beta 1 curve belonging to V. Again, alpha 1 to alpha n is a spanning set or generating set of V. This implies beta 1 can be written as a linear combination of alpha 1 to alpha n. And since with obviously at least one CI not equal to 0. At least one CI not equal to 0. Without loss of generality, we assume that C1 not equal to 0, then this imply alpha 1 curl equal to 1 by C1 beta 1 curl, C2 by C1 alpha 2 curl, Cn by C1 alpha n curl. We denote this by 1. Now, we want to prove that beta 1 curl, alpha 2 curl, alpha n curl is also spanning set or generating set of V. For proving this, we take any vector, say x curl, which belonging to V. So since x curl belonging to V, and then we know alpha 1 curl to alpha n curl is a spanning set of V, this implies x curl should be written as a linear combination of C1 linear combination of alpha 1 curl to alpha n curl. Now from 1 we see that alpha 1 curl can be written as a beta 1 to beta alpha n. Just to replace alpha 1 by this, we get, sorry, it is better to write C1 star instead of C1. This is another scalar. May not be this C1 star, C2 star, Cn stars are equal with C1 to C2 to C1, C2, Cn. So now replace, if you replace alpha 1 curl by this, then you get C1 star by C1 beta 1 curl plus C2 star minus C1 star C2 by C1 alpha 2 C2 star minus C2 star, sorry, this is C3 star, C3 star, C1 star, C3 by C1 alpha 3 curl, and the last C1 star minus C1 star Cn by C1 alpha n curl. Therefore, we see that x curl, which is an arbitrary vector in V, this again can be written as a linear combination of beta 1 curl alpha 2 to alpha n curl. Therefore, beta 1 curl alpha 2 curl alpha n curl is a linear, is a spanning set or generating set of V. So the result is, here I want to prove that the number of vectors in a spanning set is greater than or equal to number of vectors in a set of independent vectors. So here I want to mention this thing because I forgot this thing, forgot to mention this thing. So I assume the result is not true. That means number of vectors in a spanning set is less than number of vectors in linearly independent vectors. So before starting this proof, we need to assume this. So we assume this statement is false. That means the number of vectors in a spanning set that is small n, which is less than number of vectors in a independent set that is T. So now we see that this is a spanning set of T. So using same technique, same approach, we can show that beta 1 curve, beta 2 curve is a spanning set and proceeding in this way, is a spanning set of V. Now, beta n plus 1, since n less than t, so beta n plus 1 belonging to V, and this is a spanning set. So we can write beta n plus 1 curve as a linear combination of this vector. So using previous theorem, just before this, that is, the theorem tells you alpha 1 to alpha n is a set of dependent vector if and only if there exists k, which k lies between 2 to n, such that beta k can be written as a linear combination of previous vector, that is alpha k can be written as a linear combination of previous vector alpha 1 to alpha k minus 1. And here we see that this thing is happening. So we can write beta 1 curve to beta t curve is a set of linearly dependent vector. Set of linearly dependent vector. Which is contradiction? Which is the contradiction? Hence our assumptions is wrong. Therefore, n should be greater than equal to. Hence, so please tell me if you have any doubt. I'm waiting. Please tell me. Anybody tell me? I'm waiting. Please tell me if you have any doubt. Anybody? Somebody write something, please. Okay, Anushka. So, another? Okay, Shubhodip. Result, basis of a vector space is not unique. Proof. Let alpha 1 curl, alpha 2 curl, alpha n curl be a basis of a vector space V. So any vector, say x curl with belonging to V, can be written as linear combination of this vector with at least one CI not equal to 0. With at least one CI not equal to 0. Without loss of generality, we assume C1 not equal to 0. Then alpha 1 curl written as a one by C1 x curl minus C2 by C1 alpha 2 curl Cn by C1 alpha n curl. Now we want to prove that denote this by 1. Equation number 1. We want to prove that one x curl alpha 2 curl alpha n curl is a set of linearly independent vectors to is a generating set of V. So if you put these two, combining these two, this means x curl alpha 2 curl alpha n curl is a basis of V, and this justifies the fact that basis of a vector space is not unique. So for the first, that means x1 alpha 2 curl x alpha n curl is a set of linearly independent vectors. For proving this, to start with, take any vector y curl which belonging to V. This implies y curl, we know alpha 1 to alpha n is a basis, so we write this as y curl equal to d1 alpha 1 curl d2 alpha 2 curl dn alpha n. And we replace alpha 1 by this, see equation number 1, then we see that d1 by alpha 1 x squared plus d2 by d1 c2 c1 alpha 2 squared dn d1 cn by c1 alpha n squared. So this implies y card can be written as y card is a linear combination of x card alpha 2 card alpha n card. Therefore, x card alpha 2 card alpha n card is a generating set of V. Now, since alpha 1 to alpha n is a basis, so we always write I think we always write this x. And we know it is always possible. When trivial solution or Ci stars is 0. And if it is the only solution, then we can say that x card to alpha n card is a set of linearly independent vectors. Now replace x card by C equation 1 and we know that alpha 1 curl to alpha n curl is a basis of V. Hence, alpha 1 curl to alpha n curl is linearly independent vector, and this implies C1 star C1 equal to 0. Since C1 not equal to 0, because without loss of generality we assume that C1 not equal to 0, this C equation number 1, then this implies C1 star equal to 0, since C1 not equal to 0. Since C1 star equal to 0, this implies C2 star equal to 0, since C1 equal to 0. Similarly, Cn star C1 star Cn 0, this implies Cn star equal to 0. Hence, x curl to x curl alpha 2 curl alpha n curl, hence x curl alpha 2 curl alpha n curl is a set of independent vectors. First, I proved that This is a generating set. Now I prove that this is a set of independent vectors, and combining these two, we can say that x car alpha 2 car dot dot alpha n car is also a basis of V. Hence, basis of a vector space V is not unique. So please tell me if you have any doubt. Please write something if you have a doubt, no problem. If it is trivial, even then you tell me. No problem. I'm waiting. Before going to the next result, please tell me if you have any doubt. So please tell me. So the next result. Hello. কত থেকে? আচ্ছা একটু কাইন্ডলি তো আধ ঘন্টা বাদে করুন কি ক্লাসে আছে। So please tell me if you have any doubt. No problem. Okay. So next result is representation of a vector by a vector by a basis is unique. Suppose x belonging to V and alpha 1 to alpha n is a basis of V, then x car can be written as a two-way. We assume that this is a one representation and another representation is this. At least one Ci not equal to Di. Now subtracting 1 and 2, then we get since alpha 1 to alpha n is the basis of V, so alpha 1 to alpha n is a linearly independent vectors, and this implies for all I, this implies Di equal to 0. Hence, representation of a vectors by a basis is unique. And the last theorem for today's class is number of vectors in a basis is unique. So we have already seen that the basis is not unique. So we assume that x1, x2, xt, and y1, y2, yn. These are two bases, and assume that the number of vectors in a basis is not unique. So two bases of a vector space V, then since these two sets are bases of V, so since this is a basis, so we can say that this is also a generating set of V, and this is the basis. So we can say that this is also a set of linearly independent vector, and we already proved that number of vectors in a generating set always greater than equal to number of vectors in a set of linearly independent vectors. So using this result, we say that T should be greater than equal to A. Again, this is a basis. We can write this is a independent set of vectors, and linearly independent set of vectors, and this is a generating set of V, because this is a basis of V. So using the theorem, we say that this T should be less than equal to. So combining 1 and 2, we write that T equal to A. Hence proved. So this is the end of the today class. So before ending the video, please tell me if you have any doubt. I'm waiting for 5 minutes. So please tell me if you have any doubt. Suprajit says no, sir. So anybody? Then Shubhadev also no, sir. Clear. Anushka also clear. So I think, can I stop? Close the video. So okay. Thank you. I want to end the stream. So if you have any doubt, to know my number, please call me. I definitely answer your queries, and you can also email me. No, today no homework. Okay, this is a good news for you. I will give you the homework in the next class. Thank you. Thank you. Thank you. No practical.